So let's get started then. So the first speaker today is Pierre Maxted, who's going to tell us about direct effective temperature measurements from eclipsing binaries. So please, Pierre, go ahead.
Thank you. I hope you hear me okay. So thanks to Victor and the other coordinators for setting up this Exostar Redux, which gives me the chance to give you an update on one of the topics I mentioned on my Tuesday discussion session. So I have been worrying about the precision and accuracy of effective temperatures for various reasons, and one of the things I've done recently is just to sort of review how to what extent do people trust effective temperatures, the effective temperature scale for, I've been concentrating on F, G and K type dwarfs. And just sort of looking through some recent publications, you get the idea that if you're doing sort of large surveys of FGK dwarfs, you probably trust those to about 100 Kelvin in terms of that's the sort of level of systematic uncertainty that people are assuming applies to effective temperatures for FGK dwarfs that are estimated by spectroscopy typically. If you're working on fewer stars, working very carefully, you've got very good spectra, you're sort of taking care for it, and you're talking about stars closer in spectral type to the sun, that number will come down maybe to 50 or 70 Kelvin. But that's the sort of level where we are at the moment. Somewhere between typically 100 Kelvin, and you can push down towards 50 if you're working hard. Seems to be the level of accuracy of effective temperatures that people are assuming nowadays. The impact of that is that it affects the uncertainties on the stellar properties that we derive, so the masses, radii, and ages that we're deriving, and consequently, because everything about a planet is measured relative to the star, that has an impact on the uncertainty in stellar parameters. What I'm showing you here is a sort of best case scenario. This is a study that was published very recently by Bellinger et al., where they have a look at how robust are the results of astroseismology against systematic errors in temperature and metallicity from spectroscopy. So a couple of things just to note here. One is that this is a best case scenario because this is detailed astroseismic fitting. So you have a lot of information here apart from the temperature and metallicity from the spectroscopy. So this is sort of a best case where you have lots of information about the star from its oscillation frequencies. Second point to mention, the red arrow that I've added here to the figure from Bellinger is a typical uncertainty which I've taken from a spectroscopic study by Doyle et al. From WASP planets. So they're assuming 83 Kelvin is the sort of accuracy of their effective temperatures from detailed spectroscopic analysis. The reason that arrow is sloped here is because when you measure your metallicity, that also depends on temperature. So systematic errors in effective temperatures have a knock-on effect in terms of systematic errors in metallicities and abundance measurements. So the systematic error on the y-axis here is not independent of the systematic error on the x-axis. So things don't look too bad here, and in fact this is the title of the Bellinger et al. Paper. When you're looking at individual stars, the impact is small. It's comparable to slightly less than the random uncertainties. Okay, so the accuracy here from, let me rephrase that. The impact of the systematic errors on TF and metallicity here are not bigger than the random uncertainties, your precision. That's fine if you're working on a few stars. The problem comes if you're dealing with large samples, which is increasingly the way we're going, right? The way that exoplanet science is going is to generate large samples of planet hosting stars and to look for trends. So we're interested in questions like how do planet properties vary as a function of the stellar metallicity? How do planet properties vary as a function of the stellar age? And so here we see the issue with systematic errors in temperature. If you have a systematic error in effective temperature, that doesn't average out, all right? That will give you some sort of spurious trend with metallicity, mass, age. All these things are interrelated. Very hard to pull apart the impact of systematic errors in temperature if they are correlated with something else, if there's some confounding variable. So if, just to make up an example, if your effective temperature scale for metal-rich stars is inconsistent with your temperature scale for metal-poor stars, that will give you a spurious trend. So that's one reason to sort of work a little bit on the effective temperature scale. The other reason I've come at it is because it's a limiting factor when we're calibrating stellar models using eclipsing binaries. Just to go over quickly where this uncertainty originates. So I'm starting here, going right back to basics with the definition of effective temperature at the top there, in terms of the Stefan-Boltzmann law and the luminosity of the star. And then you divide both sides of that by 4 pi times the distance squared to get an expression for the effective temperature in terms of the bolometric flux, the integrated flux at the top of the Earth's atmosphere, and the angular diameter. These angular diameters for direct effective temperature measurements come almost exclusively currently from interferometry, which is hard. For a star similar to the Sun at 10 parsecs, the star is going to be less than a milliarc second across. And so that's essentially the main reason why there seems to be this 2% uncertainty in the effective temperature scale. Just to show you, I'm going to flip forward here to show you where that 2% uncertainty, how I've estimated it. It comes from this. It comes from, if you look at recent publications of published interferometric angular diameters for stars with angular diameters of about 1 to 2 milliarc seconds, there'll generally be a comparison to previous studies, and those will generally show an extra scatter or some sort of systematic error at the level of about 0.05 milliarc seconds. That seems to be, you can do that more quantitatively, but just by eye you can see that's about what you've got here in terms of the extra scatter that you're seeing from repeated measurements compared to the sort of quoted uncertainties. Now doubtless this will improve, all right, so the instruments are getting better, the baselines are getting longer, but we're not going to see an order of magnitude improvement in this. There just aren't that many bright nearby solar type stars that are well resolved. So this has got me thinking about whether we can do better with eclipsing binaries, because with eclipsing binaries we can measure the radii to 0.5% or better, and now that we've got Gaia parallaxes, we'll have the distances to about 1% at 250 parsecs, and that will improve even more by the time we get to the final Gaia data release. So that will give us some very good measurements of the angular diameters, theta, for stars in eclipsing binaries. So if we can get these F-bol measurements, if we can split the light apart into the contributions for the 2 individual stars, there's a way here to get good effective temperature measurements, an alternative way to do it, that we can use to improve or check the interferometric scale. Just some very quick theory on eclipsing binary stars, just to persuade you that we really can do very precise masses and radii. This blue curve here, which looks like a textbook figure, these are real data for a real eclipsing binary that come out of the Teft mission. And you can't even, the noise here is at the sort of, you can't even see it. So what you measure from a light curve like this, which is a nice total eclipsing binary with no complications, you've got 4 observables here. You've got the 2 eclipse depths, you've got the total eclipse duration, and you've got the duration of the flat part of the eclipse. So there's 4 observables, and you can turn those into 4 geometrically measured quantities. And the ones we're mostly interested in here are these fractional radii, the radii of the stars divided by the semi-major axis, and you get the inclination and the flux ratio. And the flux ratio we're going to use in a minute. The orbital inclination is always going to be very close to 90 degrees anyway. So that's sort of the theory. Here it is in practice. I mean, there are some complications here to do with Lindgartening and detrending your light curves and so on. So when the test data appeared for this very well-known eclipsing binary, AI-Phi, I basically sent an email to everyone I knew who published analysis of an eclipsing binary recently, and asked them to analyze it independently. And by the time we sort of sorted out a few problems, that top right diagram shows you how well these key quantities, R1 over A and R2 over A, how well they agree between different methods, different detrending methods, different researchers. And the agreement there is better than about 0.15%. There's also a nice thing with AI phi, this being a relatively nearby eclipsing binary, we actually have a parallax measurement for this star directly from it's resolved on the sky. So we have an astrometric parallax for this as well, which agrees very well with the Gaia DR2 parallax corrected for its 0-point error. So that's all looking pretty good in terms of R1 over A, R2 over A and parallax. You then also need the masses of the stars from its spectroscopic orbit to use Kepler's law to get A, and that turns your fractional radii into real radii. This diagram on the left is just to point out that if you take measurements of the semi-amplitudes of the spectroscopic orbits, basically the orbital speeds of the two stars, and you look at measurements that have been made with Echelle spectrographs by 3 independent teams, 3 different measurements by 3 different methods and so on, they all agree amazingly well. The old measurement there is made with a sort of hardware cross-correlation thing from more than 30 years ago now. But with modern instrumentation, it's possible if you want to, you've got enough time, and you just throw the telescope time at it, to get your masses down to 0.1%. So your radii can, if in principle, with good light curves, can be again at the sort of 0.1% level. So then what we need to do in order to turn this into an effective temperature is split up the flux. In the top here you see the 2 spectral energy distributions. In the middle you see all the filter band passes that we use to measure the combined magnitudes. In the bottom panel you have all the flux ratios. So what you need to do in order to work out the temperatures is adjust those spectral energy distributions at the top so that they fit all those fluxes and flux ratios. So what we do here, to avoid just fitting a spectral energy distribution, and also to avoid just fitting an arbitrary function, what we use model spectral energy distributions out of some grid of stellar models, and we allow them to be distorted by a series of Legendre polynomials. And then this gives us these spectral energy distributions that we can then optimize to fit all the fluxes and all the flux ratios and use to calculate the effective temperatures in a sort of fully Bayesian way, allowing for all our priors on the reddening and so on. So this is a nice way of having an integrating function, a function you can integrate, which has sort of realistic looking spectral energy features in it, like spectral lines, but without just doing a spectral energy distribution direct fit, which would just give you back the effective temperature you put in. So here's the punchline. So when you do this for a very well-studied binary, you can get your temperatures down to 16 plus or minus 16 Kelvin for the cool star, plus or minus 22 Kelvin for the hot star. There's an additional systematic 11 Kelvin error here, which is the uncertainty in the flux scale for stars. Okay, so we're tied to the CalSpec flux scale that's determined for the HST, and there's some uncertainty on basically, how many photons per second do we measure for Vega at magnitude 0 at some wavelength. So this essentially that's the punchline, right? This works really well. So there's lots to do with AI phi now. Obviously, we'd like to compare these temperatures, compare it to what you get from fitting the spectra. So we have some observations scheduled with UVES coming up to observe the star in eclipse, so you can get some good spectra. And then we can go on, measure the metallicity and compare to models to see how well we can use that to constrain the stellar models. And obviously, we'd like to do this for more stars. If I just have a minute, I just want to say that if you look at the Kepler K2 analysis we did of 3 Kepler K2 fields, looking for interesting looking binaries, we find typically 3 interesting binaries, meaning like nice long period FGK dwarfs with total eclipses. You find about 3 of those per Kepler K2 field, and you sort of scale that up to the sky, the whole sky. There's probably about 1,400 of these things on the whole sky. So there's lots and lots of targets to go at here. it may not be as high as 1,000 or 2,000 because you've got to worry about the reddening, which I haven't talked about a lot here. I mean, there's ways to handle that reddening, but it might be that we can't work with it when the reddening is very high. We haven't really investigated that a lot yet. But certainly there's going to be, certainly hundreds of these stars potentially that we could apply this to. And just very briefly, you have to be able to measure the total flux. There will be a hot limit where you just can't measure the flux because it's all in the UV where you can't measure it. But it looks like that limit only cuts in when you're talking about B stars. We should be able to apply this all the way through the spectral type F, probably well into the A's. Things will probably get dodgy because we can't measure all the flux by the time you get up to B. That's it.
Thank you so much, Pierre. Do we have questions for Pierre? We have time for one or two quick questions. I see one is written on the chat. Josh Pepper asked if you can obtain absolute flux calibration for an eclipsing binary target in a single bandpass. Will that significantly reduce the systematic uncertainties?
Well, we sort of already do that, and most of the flux is in the optical, and we catch that through Gaia. So we use photometry all the way from the UV through the optical and into the near infrared to measure the total, the combined flux from both stars. So that's done using just sort of catalog photometry from Gaia, WISE, 2MASS, and so on. You could, in principle, do this by taking sort of low resolution, well calibrated spectroscopy through the eclipses. That would be really nice data to work on, but harder to work on it, and I don't know if it's necessary to get this sort of precision.
I have one raised hand, Lokesh. I think she wrote the question. Just one more question is, can this method be extended to longer wavelengths to study planet formation?
Can this
method be extended to longer wavelengths to study planet formation?
I don't know, because I'm not sure how you would study planet formation with this method. I mean, essentially it's...
then we can maybe think about that for the discussion part.
Yeah.
Thank you so much, Pierre. I don't know if we give a virtual class to Pierre, but thanks so much for your talk.